In Chapter 4, our primary focus is going to be looking at the different ways that molecules and compounds can use the octet rule. Now, to talk about this, the book is going to spend a little time talking about why molecules form and the rules that molecules form. It's important to know that these are very simplistic rules, and actually they're going to contradict what we do in Chapter 5. So don't get too attached to these rules. In fact, I would not spend any time more than what we're going to do in the slides, which is just explaining the theory in brief. We're going to go through molecular drawing pretty heavily on the next exam, and so I would worry about that then. For now, just understand the difference between ionic and covalent complexes and how we name them and why they're different. That's it. That's all we need to do. In the last third, we're going to look at moles with compounds and how we can use moles to find the formula of compounds. So that's a little different, but it matches up with what we did in the end of Chapter 1. All right, so 5.1 just really quickly introduces the idea that if you change from elements, and you change those elements into a molecule of something new, this is a chemical change. So like all chemical changes, this new substance has brand new properties. And in a few chapters, we'll discuss where those properties come from and why they're so different for these compounds. But for now, we'll just say, again, new chemical structure, new chemical compound. So what we're going to say is that compounds form in two primary ways. Okay. Either they go through covalent bonding, in which case we're going to share pairs of electrons together, and we're going to get that octet. And what you're going to see through the next several chapters is that the octet is the grand goal of every chemical compound. We're trying to get an octet around every atom. So by sharing electrons with hydrogen, oxygen has access to 8 electrons. And by the way, hydrogen also gets access to 2, which is its full energy level. So that makes hydrogen happy too, even though it's not 8 electrons. Okay. Now, the next thing we're going to point out is that ionic bonds are also trying to get a full octet, although they're going to do it in a very different way. Instead of sharing these electrons, the chlorine is going to steal the electron from sodium to form an octet. And sodium actually loses that electron and becomes the octet in the previous shell. It's a 2s2 2p6 octet. And as a result, they both reach an octet. Now, there is no true bond holding these things together, but we say they're charge stabilized, which means the two charges attract each other and NaCl stays together even though there isn't a true shared bond. Now, the book introduces this a little differently than I prefer to. Okay, but let's explain this. So what we're looking at on the left is the Lewis symbol for all these elements. Now, a couple of things. One is that we get these Lewis symbols from your valence electrons. So essentially what we're doing is we're taking your number of valence electrons and we're splitting them up evenly among 4 orbitals. Okay, so like carbon, for example, its valence shell is 2s2 2p2. Now, turns out keeping these electrons in the lowest energy orbitals is not the best way to configure bonding. And so when these things try to bond, they actually split these electrons evenly among the valence orbitals. So if we just say 1 orbitals on each side, I'm going to split the 4 valence electrons into 1 electron for each side. Nitrogen has 5. That's going to leave it with 1 paired side and 3 unpaired electrons. Okay, so every side that has only 1 electron can be used to make a bond. And so carbon is almost always going to have 4 bonds. Nitrogen is almost always going to have 3. Now, I do want to point out that this is a very simplistic way of looking at bonding. And we're not going to stick with this for very long. So don't spend too much time looking at this picture. Okay. Well, we can see, even with these very simplistic pictures, why bonding occurs. Fluorine has 7 valence electrons. That gives us 3 paired sides and 1 unpaired electron. They merge together to form a bonding pair, and that's between the two fluorines, and then the fluorine is surrounded by lone pairs. Now, these paired electrons are called lone pairs because they can't actually be used to bond to anything. Okay, that orbital is full. It has its maximum electrons, and so no bond can be made. Now, if we look at that middle picture here, you can see that each fluorine has access to a total of 8 electrons. All 4 sides, i.e. all 4 orbitals, are completely filled. Now, to clarify which pair is bonding and which pair is non-bonding, or a lone pair, we turn the bonding pair into this line. Keep in mind that the line literally means 2 electrons, okay, shared in a bond. We draw this bond like a straight line. You can kind of think of it like a bungee cord. And just like a bungee cord, this line is not stuck. It's not a specific length, but will actually kind of bounce back and forth. So like a little bit of a bungee cord / spring, a little bit. Again, if you treat the line as 2 electrons, each fluorine is surrounded by 8, it satisfies the octet rule. Okay, again, carbon has 4 unpaired electrons. It prefers to make molecules with 4 bonds. And in fact, my organic teacher used to always joke 3 things in life are certain: death, taxes, and carbon has 4 bonds. Now, we also have things called double bonds, and you can see why in this picture. Oxygen has 6 valence electrons. If it's going to bond with another 6 electrons, the only way to get to an octet rule is by sharing 2 pairs of electrons. Okay, and so we draw that as a double bond, 2 lines signifying the double. Same thing with nitrogen. We can see why nitrogen forms a triple bond, because the only way to get to an octet is by sharing 3 pairs of electrons. Okay, so you get 3 lines, 2 lone pairs, you get a triple bond. So the real question here is, how do you decide when to use these double bonds? And this is a problem that this system really doesn't address. So as a result, we're not really going to practice the drawing method in Chapter 5. We need to look at a different way of arranging these electrons to get the most stable molecule. Not necessarily the one with the best atom, but with the best entire molecule. So for that reason, I say don't bother drawing anything in Chapter 5. We will cover all of this in Chapter 6 with a different system. And the problem for people who learn the system in Chapter 5 is they have trouble adjusting to the system in Chapter 6. So don't do any of this section. Okay. So what we want to do instead is focus on how we name these things. So no matter what the bonds look like, right, we can ignore double versus single bonds for now and just focus instead on the structure. And what we said is because molecules always have the same structure, and that structure is determined by the number of atoms in the molecule. The molecular compound naming system is really designed to focus on the number of atoms in that molecule. And that makes the naming system here very simple. So this system is known as the binary molecular compound naming system, right? Because we are only going to look at compounds that have only 2 types of elements. Things with more than that use a more complicated naming system that we're going to ignore. It's covered in the last section of this chapter, but it's also not used until organic chemistry. Now, there is a specific order in which the atoms are supposed to go. This looks really complicated on the piece of paper as written on this slide. If you look at the periodic table, it's essentially going from the left side of the periodic table to the right. But it's important to keep in mind that I'm either going to give you the name, which is already in the correct order, or I'm going to give you the formula, which is already in the correct order. So memorizing this system isn't super important. There are times when you're answering questions in MyLab and Mastering when they will expect you to get the answer in a specific order, or else it won't accept the answer, which is kind of annoying. If that comes up, just flip back to this slide. Otherwise, on the test, it's not going to make a difference. So graphing the correct order on the periodic table makes this a little bit easier. With exception to hydrogen, we go from the left side of the periodic table to the right side of the periodic table in order. Now, the next thing I want to point out with these non-metal compound names is that, sure enough, all of these compounds we're talking about forming molecular structures are all nonmetals and metalloids. We're not talking about metals on this chart at all. And that's really important because metals are primarily going to go through ionic bonding. So anytime a compound is made out of nonmetals and metalloids only, it's always going to be a molecular formed compound. Again, we'll talk about the ionic more a bit later, but that's just a good thing to keep in your head for now. What we're primarily going to focus on in this chapter is naming binary compounds. The book gets into a lot of common names, and I have a study sheet online that you can look at. A lot of those I'm not going to spend any time on. We just don't use them very much here. They're not very helpful. So that's it. Now, binary compounds. Basically, these are compounds made up of only two types of elements. The first element gets its original name and only gets a Greek numerical prefix if there's more than one. So if you look down below, carbon has only one and carbon dioxide. Silicon has two, so it's disilicon. Phosphorus has one, so just one. Now these Greek numerical prefixes I'm going to give to you. You don't need to memorize them, but you probably want to use them enough that you're comfortable with them. Then you're much less likely to make a mistake. Second element is always going to get a Greek numerical prefix. And we're going to change the compound, the element name, by adding IDE to the end. So carbon dioxide, disilicon, tetrachloride, phosphorus, pentafluoride. And a great example of how the second one always gets a Greek numerical prefix, but the first one doesn't, is carbon monoxide, right? Both have one element, but the second one will get the mono. The first element does not. Okay, so these are pretty easy. Just look through that list, figure out the names, and we'll walk through it. Okay, when you're ready, we'll go through the list. These, for the most part, are pretty straightforward. P2O5 is diphosphorus pentaoxide. A lot of times we get rid of the A just to make it easier to say, so we don't have two vowel sounds back to back. So diphosphorus pentoxide. Silicon tetrabromide, trisilicon decaphosphide. S2O4 is disulfur tetroxide. Arsenic hexachloride, and diantimony heptaiodide. Alright, I haven't written in the answers for these, but they're pretty simple. I'll walk you through them really quick. I'll give you a 5-second pause, so go ahead and pause the recording until you're ready. Okay, set. Trinitrogen hexasulfide is N3S6. Triboron heptafluoride would be B3F7. Dihydrogen monosulfide is H2S. Phosphorus pentabromide is PBr5. Ta-da! So there's one group that's not explicitly covered in the book, and that is naming elements. And I think one of the reasons why it's not explicitly covered is because it's supposed to be self-explanatory. It's not. So there are 7 elements in the periodic table that all form molecules instead of single atoms. And those 7 are H2, N2, O2, Cl2, Br2, and I2. Again, keep in mind that these are all in their elemental form. Since they're in their elemental form, they just get the elemental name. We call them hydrogen, nitrogen, oxygen, chlorine, bromine is a liquid, and iodine is a solid. Okay, so we don't get any prefixes on these things because these are not compounds. So they do not follow the compound naming system. So I love to put these on a test, right? What is the name of hydrogen? H2. And all people have to do is write down hydrogen or hydrogen gas, and they get the correct answer. People love to put down dihydrogen. Again, it's not a compound. It doesn't get the prefix naming system. So memorize these. We're going to run into them all the time. Okay. What we're going to talk about is ionic compounds, literally a compound made out of ions. And it's worth bringing up that these are very, very different from covalent compounds. Whereas covalent compounds have chemical bonds holding these things together. These ionic compounds, or salts as we commonly refer to them, are entirely made from attractions between the positive ion and the negative ion. And, this ideal state of ions also makes these chemicals much less reactive. So in their pure elemental state, sodium explodes in water and chlorine is mustard gas. But in their ionic state, they're much more stable. We eat NaCl all the time. Okay, so in a salt, what you have is a grid of positive and negative ions. The positive ions surround the negatives surround the positives, and the attraction between these ions is what holds the salt together. It should also be noted that this grid essentially occurs over and over again, essentially to infinity. In order to make a salt cube that you can actually see, it requires trillions and trillions of these ions stacked on top of each other. This is also what gives salt a very squarish appearance. As we talked about last chapter, we can predict the type of ions that tend to show up based on the octet rule. Metals and things left of the periodic table tend to form positive charges. And for main group elements, the charge is related to how many valence electrons they have. So if you have one valence electron like sodium or potassium, you tend to lose that electron to become a +1 charge. If you have two valence electrons like magnesium or calcium, you tend to lose 2 electrons. These are all called cations. Okay. On the right side of the chart, we have anions, which are nonmetals, which form negative charges to get their full valence shell. Now, ignore the transition metals for now. We'll talk about them later. And there are several things that sometimes form charges, but group 4A never forms a positive or negative charge. It's stuck in the middle. We're going to ignore them. There are exceptions to things like lead and tin, which are down here, but we're not going to spend much time with them. Gallium and indium sometimes form +3 charges as well, but it's more complicated for reasons we'll get into later. So if you want to name these ionic compounds we've been building, these names are really derived from the names of the individual ions. So we're going to talk about how we name these ions. And we're going to start with monoatomic cations. And what monoatomic means is just single atom cations, okay, what we've been working with already. So cations, again, just means positive charge. And these ions are named very simply. All you do is you add ion to the end of the name. So sodium ion, calcium ion, aluminum ion, rubidium ion, etc. And these names are very simple because you should have memorized what these ions are. So sodium is always a +1 ion. Aluminum is always a +3 ion. And so that way, just by saying calcium ion, everybody knows you mean a Ca+2. It's always the same thing. We'll get to transition metals later, but they're much more complicated. Monoatomic anions, again, single atom negative ions, they do get a change. They go from ene to ide. So chlorine becomes chloride, bromine becomes bromide. The -2, -3 are a little bit more complicated. Sulfur becomes sulfide, oxygen becomes oxide, nitrogen becomes nitride. All right, because K is positive, all we do is add ion to the name, so potassium ion. The other two ions are negative, so we're going to add the IDE. O2- is the oxide ion. Chlorine will become the chloride ion. All right, now based on these names, see if you can figure out what the ion is. You're going to need your periodic table to just find these things. Calcium ion is in group 2, so we'll always form a +2 charge. Again, we know it's positive because there's no IDE sound. Selenide, on the other hand, tells us that this is a nonmetal anion, so it's going to be negative. It's in group 6, so it needs 2 extra electrons to get to that octet rule. So since ionic compounds are made up of ions, the naming system is completely and totally based on their ion names. So sodium chloride is made up of sodium ion and a chloride ion, so the formula name is just sodium chloride. Now, the formula for these structures is dependent on charge. So we're going to say a stable salt always has equal amounts of positive and negative charge to keep the overall salt stable. So a sodium ion we know is +1 ion, and a chloride ion is -1. And so those charges already balance, and so we're going to have 1 sodium per 1 chloride. Now, we're always going to have the metal formula first, and then the nonmetal. And when we put these ions together, we're no longer going to write the charge anymore because that charge is essentially neutralized or equalized. So our formula is just going to be Na. So metal first, chloride, nonmetal second. When it comes to magnesium chloride, we know magnesium always forms +2 ions. And chlorine always forms -1 ions. And so now we need more negatives to balance out the 2 positive on the magnesium. So if we have 2 chloride ions, that makes the charges equal. And so we now have a formula of MgCl subscript 2. Now, it's important to keep in mind when you look at these formulas that we do not include the charges once they are part of a compound. That's because we say those charges essentially equalize out to make the stable overall compound. I just want to take a second to point out that these crystal structures are going to look a little different than the sodium chloride structure we saw earlier. This is a crystal lattice which expands in all directions. What we're really looking at is the magnesium ions in gray, the little tiny ones, and the chloride ions in green. And it's a little tricky to look at, but if you kind of look at each group at a time, you can see that there are approximately 2 greens for every 1 gray. Now, again, this is going to continue in all directions, essentially infinitely for billions and billions of molecules. But you can kind of see that pattern repeating where every magnesium is surrounded by 2 equivalent chlorides. We'll do the exact same thing for sodium sulfide. Sulfur atoms always form ions with a -2 charge. Sodium ions always form with a +1 charge. And so therefore we're going to need 2 sodiums for every sulfide. And so that's going to give us the subscript Na2S. So if we say sodium nitride, that means we have a sodium ion, which is +1. We have a nitride ion, which is -3. And so therefore we need 3 sodiums to counteract the nitride. And we'll have a formula of Na3N. Based on these names, determine the ionic charges on each of these ions, and then determine the stable ionic compound that will form. So we know that magnesium is a +2, and bromide is in group 7, so it would be a -1. So the formula should use 2 bromides, and so would be MgBr2. Potassium oxide. Potassium is +1, oxygen is -2, so we need 2 potassiums per oxygen. Lithium nitride, lithium is always +1, nitride is -3, so it's 3 lithiums per nitride. So naming ionic compounds is very, very different than naming molecular compounds. Okay? In the molecular compound name, we use the prefix system. Okay? In the ionic naming system, what we're going to do is say, okay, there is no molecular entity here. What we have is a lattice of ions stacked on top of each other. So if you want to know what that lattice is going to look like, we have to know what the two ions are. And so that's what the name is. It's just what two ions are involved. So NaCl has a sodium ion and a chloride ion, so it's just sodium chloride. Lithium and oxide are two ions, so it's just called lithium oxide. And that's it. Take a quick second and name these salts based on the ions available. Again, the number of ions does not matter here. Okay, so again, the number of ions doesn't matter. We're just looking at what type of ions are available. We have a calcium ion and an iodide ion. +2 and 2 negative 1s makes calcium iodide. We have 2 aluminums and 3 oxides, gets us to +6 and -6, 2 +3s, 3 -2s, but it doesn't matter, right? It just, what kind of ions do you have? Aluminum ion, oxide ion, we just call it aluminum oxide. Mg is +2, sulfide is -2, magnesium sulfide. Again, I want to point out that none of these names are capitalized in chemical compound names. Now, when it comes to the polyatomic ions, we have a slightly more confusing problem. What these are is a group of atoms combined together like a molecule. But unlike a molecule, they end up with an overall positive or negative charge. And so when they get into forming a larger compound, they form much more like ions than they do like molecular compounds. So we have a group of names here, and so nitrate, nitrite, cyanide, bicarbonate, chlorate, chlorite, hydroxide acetate. I've organized this group by -1, -2, and -3 charges. And so when you look at these things, you see this giant list of names and numbers, and people tend to freak out. What I'm going to say is instead is, kind of don't pay attention to all of this. Only focus on the charge on the very end. Because the charge is really what we're focused on. How are these two ions going to stack together? The other thing I like to point out is that most of these ions end in ate or ite. So anytime you see ate or ite, that tells you, oh, this is a polyatomic ion. And that's different from the monoatomic ions we learned earlier, which end in ide. Now, there are 2 exceptions to that, or rather 3 exceptions. Cyanide, hydroxide, and those 2 ions we'll see fairly often. Peroxide we won't, but hydrogen peroxide, you can think about what that means. Now, the one thing that's different here is that we do not make you memorize these names. However, we are going to use a lot of these very, very often. And so the more familiar you are with them, the better off you'll be. I'm going to give you this list on the test, but you're going to want to practice a lot. So for example, the ions we're going to see a lot are nitrate, carbonate, sulfate, and phosphate. Those are ions that we're going to see 15 or 20 times this semester. So, you don't necessarily have to memorize them, but I would be very, very well acquainted with them. Now again, determining the salt formula from the name is very, very simple here. Okay, when you see the name sodium nitrate, again, because there's a metal, sodium, we can say it's an ionic compound. And so we know the sodium is +1, the nitrate is -1, 1 and 1 are stable together, so our formula is just NaNO3. Again, we're just focused on the +1 and the -1. Ignore the 3 as best you can. Okay. Now, when you say a name like barium nitrate, okay, we have a barium ion is +2. That means we're going to need 2 nitrate ions to have equal positive and negative charge. And so the formula is going to be Ba brackets NO3 bracket 2. And that tells you that you literally have 1 barium paired with 2 individual nitrate ions. Okay, we can't really change that formula or write it in a different way because it would mean something different. For example, if you just wrote BaN2O6, that implies that we have an N2O6 ion, which is not true. If you don't include the brackets, it's not really obvious where that 2 is supposed to go to. So again, by putting brackets around nitrates, we say we have 2 individual nitrate ions per unit of this salt. So go ahead and really quickly determine the formula of these salts based on the name. Okay. So magnesium nitrate, magnesium ion, we need 2 nitrate ions to counteract the positive charge, so Mg brackets NO3 2. Sodium sulfate, we're going to need 2 positive 1 ions to balance the negative 2 on the sulfate, so it's just Na2SO4. Now, because there's 1 polyatomic ion, we don't need the brackets. If you include them, I'm not going to count it wrong, but we don't need them. Calcium phosphate, calcium is a +2, phosphate is a -3, so we're going to need to go to -6 and +6 again. So 3 positive 2's gives us calcium 3. Brackets on the phosphate, we're going to need 2 phosphates to get to -6, so PO4 2. Okay, try this the other way around. Determine the name of these ionic complexes based on the formula. Quick note, some of these things are not polyatomic ions, some of them are, so look at the list for the ones that are, and we'll do the rest. The one ion we haven't seen very much is NH4, which is a positive ion, so definitely check the list for that one. Where this really gets complicated is the transition metals. Now, all transition metals are metals, and they are all positive ions. But they don't follow the normal electron-ion rules that the rest of the periodic table follows. And so most transition metals can have multiple ionic charges. And now we label this with Roman numerals. So the copper 2 ion has a copper 2 plus charge. Copper 1 ion has a copper plus charge. Now, this gets confusing because when we say, like in the top right-hand corner, copper 2 chloride, we're not referring to the formula, we're just referring to the charge. So in the case of copper 2 chloride, copper 2 plus does require 2 chlorines to form CuCl2. Okay? But in the case of titanium 2 oxide, titanium is 2 plus, oxide is 2 minus, the charges are equal, no 2 is needed in the formula. Again, the Roman numeral indicates the charge. It does not necessarily indicate the formula. Okay, so try these 4 out. Again, figure out what are the formula and the charge for each metal and each ion, and then determine the formula. All right, ready? Okay. Nickel 1, S2 minus, so Ni2S. Iron 3, Cl minus, so FeCl3. Cobalt 2 plus, SO4 2 minus, oh, it's not on here, CoSO4. Mn plus and PO4 3 minus, the only way to get equal amounts of charge is to have Mn3 PO4. So when you have to name these transition metals, that's when these get really, really difficult. And the big problem is that we have no idea what that metal charge is looking at the formula. So we have to work backwards. We know that nitrogen always has a charge of -3. And based on the formula, we know that there are 3 nickels balanced against it. And since in salts, we always have to have a 0 overall charge, that tells us that each nickel must be +1. And if each nickel is +1, that means the name has to be nickel 1 nitride. Okay, so we're not naming the number of nickel ions. All we're naming is what is the individual charge on each nickel ion. And that's really hard to get used to. So kind of keep that in mind as you practice these problems. So again, for FeI3, we know there are 3 iodide ions, and we know those are each -1. So iron must be +3, and so we call it iron 3 iodide. For NiCO3, we know that this is a carbonate ion, and if you look up the charge on the chart, you see it's -2. Since there's equal amount of nickels and carbonates, then nickel must be +2, and so we call this nickel 2 carbonate. The last one is the most tricky. We have 2 sulfurs per palladium. Since each sulfur is -2, palladium must be the opposite of that total charge. So palladium must be +4. So we'd call this palladium, Roman numeral 4, sulfide. Okay, I also want to point out that we can have these salts called hydrates. And I probably will not ask you a lot about this. But what we do is we just add the number of hydrates with the prefixes from the compound system. So magnesium sulfate heptahydrate just says there are 7 molecules of water mixed into this salt for every 1 magnesium sulfate. So cobalt 2 chloride with 6 waters would be hexahydrate. Now, where this gets really tricky is that on this test, I'm going to switch back and forth between molecular compounds and ionic compounds. And I expect you to know which one is which. The easiest way to tell is that molecular compounds do not contain metals. Okay? The ionic compounds do. And that's the biggest difference. Now, the naming systems for these are completely different. You have to keep track of that binary molecules are molecules. They're what you think of as molecules. And as such, we are going to describe them with prefixes. What does the total formula look like? Carbon dioxide, 1 carbon, 2 oxygens. Since ionic compounds have trillions and trillions and trillions of atoms stacked on top of each other, we don't use any of those prefixes. We don't count the numbers of atoms at all. We figure out what is the charges that need to stabilize. Now, this is even uglier when you see those transition metals, because then they need to get a Roman numeral. Okay? But just think, things like sodium chloride, lithium chloride, LiCl, sodium oxide, Na2O. All of those things have a metal at the beginning of the formula, and so they use the no prefixes system. Okay. So when you're doing a problem set like this, first of all, I'd figure out if it's an ionic compound or a molecular compound, because that will make a big difference which one you use. The next thing I would do is try and name it accordingly. If it needs prefixes, put in prefixes. If it doesn't, figure out what's going on. Now, this is an incredibly difficult problem set. There's also an element I've snuck in there, so name the element accordingly. Okay. So when you're doing a problem set like this, first of all, I'd figure out if it's an ionic compound or a molecular compound, because that will make a big difference which one you use. The next thing I would do is try and name it accordingly. If it needs prefixes, put in prefixes. If it doesn't, figure out what's going on. Now, this is an incredibly difficult problem set. There's also an element I've snuck in there, so name the element accordingly. Okay. So when you're doing a problem set like this, first of all, I'd figure out if it's an ionic compound or a molecular compound, because that will make a big difference which one you use. The next thing I would do is try and name it accordingly. If it needs prefixes, put in prefixes. If it doesn't, figure out what's going on. Now, this is an incredibly difficult problem set. There's also an element I've snuck in there, So name the element accordingly. Okay, so this is also true for molecules. 1 molecule of water weighs 18 AMUs. So by Avogadro's number, 1 mole of water weighs 18 grams. And the way we do this in the lab is we just go to each of these components and we say, okay, mole of water contains a mole of oxygen and 2 moles of hydrogen based on the formula. And so 1 mole of oxygen, according to the periodic table, is 16.0. 1 mole of hydrogen is 1.0. And there's 2 of them, so there's 18 grams per mole of water. That's also true for something like C2H6. By the way, this is known as a molecular weight. So MW for short. Again, all we do is add up all the parts, and that tells us the weight per mole. So there's 2 carbons, each weighs 12.0. There's 6 hydrogens, each weighs 1.0. And so it's a total of 30 grams per mole. And that, by the way, is also equal to Avogadro's number. Okay, so that's very, very helpful to get back and forth between grams per mole. So this is essentially going to be a conversion factor. So formula weight is the same idea. Technically it's different, but in practice it's used exactly the same way. Okay, so we're looking at a salt, CaCl2. Again, the difference between a salt and a molecule is that a molecule is a single structure containing only a few atoms, whereas a salt, like calcium chloride, contains billions and billions of atoms in a lattice arrangement. The key here is that calcium chloride has a single formula unit, so the simplest possible ratio of calcium to chlorine, and that's going to be our formula weight. Okay, so when we say a mole, we're really talking about a mole of CaCl2 formula units. But realistically, we count it up the same way. The formula is CaCl2, there's 1 calcium and its periodic table weight, 2 chlorines and its periodic table weight. They add up to 111.1 grams. That mass is equal to 1 mole of CaCl2 units. Okay, now, one thing I do want to point out here is that in all of these slides, I've taken the units out to the tenths place. That is the minimum I require to get good results. If you round off that tenths place, you're generally going to get a much worse number. And this will show up in the labs if you're not remembering to go out that far. Again, in things like carbon, it's 12.0, so it's not a big deal. But in things like chlorine, rounding off that 5/10 is going to cause problems later on. So go out at least that far. You can go out farther if you want. You can go out to the hundredths. You can go out to the thousandths if you choose to, but generally it's not going to make a big difference. So using the periodic table, get the average mass for each element and add it up to give the formula weight or molecular weight for each of these compounds. Afterwards, flip over the slide and see the next answer. So I did this first one a couple of different ways just to kind of show you how this works out. The common mistake most people do is they round off to the ones digit. And in this case, it does give you, 3 sig figs. But you end up off about 2 to 3% from what I consider 134.5 or 134.45 to be the right answer. So it's much better to go out to at least the tenths. If you do that, you get 134.5 grams. Now you can go out farther than that if you want. I will note that if you go out farther than that, make sure you only go out as far as both numbers have digits. In this case, you can go out as far as the thousandths place. If you do that, we get 134.452, which, as you notice, is extremely close to the number we have. We are, within rounding 4 digits up above. And so you're looking at a, 0.02, 0.03% difference. It's pretty small. So again, go out to at least the tenths is my best suggestion. Now, with carbon, hydrogen, and oxygen, again, generally chemists go out to the tenths place. If you want to go out to the hundredths place, right? There is a small difference. Hydrogen is actually a little smaller than 1.01. It's 1.008. But if you round it off, it comes out to 44.06. 44.1 is technically a better measurement than 44.0, but it's actually not as big as even looks here. So either 44.0 or 44.1 or 44.06, I would accept all of those. Okay, so when it comes to moles, what we're going to say is the number of moles is directly relative to the number of atoms present. And so we can say, all right, we can use these moles to compare with vastly different atomic masses. We can say, all right, how many groups of this chemical do I have? Which is really going to be important when we start talking about moles heavily in chapters 7 and 8. So the first thing I have to do here is add up the atomic weight for nitrogen and the 3 hydrogens. Again, I rounded up the hundredths place of oxygen to get to 1.01. Again, that works out to 17.0 or 17.04 grams per mole. Again, we have to do this on our own. This is not given to you, but you have to look at the periodic table and be able to see the gram per mole as a conversion factor. Since I'm starting in grams, I'm going to divide by grams. I'm going to multiply by moles, and that tells me how many moles of this molecule I have. So using the molar mass as a conversion factor, determine the answer to both of these questions. So the key to this problem, of course, is finding the molecular weight, or in this case, it's a formula weight. Actually, this is a salt. So the 40 grams per 1 mole of NaOH. Since we're trying to find the grams in the first question, grams will go on top, moles will go on the bottom. Since we're trying to find the moles on the second question, the moles will go on top, the grams will go on the bottom. And that's it. So that's the end of chapter 3.3. I strongly recommend you practice as many of these mole problems as possible. Again, we are going to use this a lot in the second half of chapter 3. And the more comfortable you are with these problems, the easier the second half will get. Mass percent composition is a real simple way we use to identify compounds. And basically what it looks at is what is the percentage of mass that comes from one element in a compound. Say, for example, you have a compound that is, 40% carbon and 60% oxygen. Okay, well, it turns out that these numbers are often very indicative of specific compounds. So if you can measure the percentage mass of all the elements, it often is used as a way of identifying which compound you're working with. So to find the percentage of an element, all you do is you take the total formula weight of the compound, and you put the number of that specific atom times its atomic weight over the total formula weight times 100. So we can go back to C2H6, which we said was 30 grams per mole. If you're looking at the percent composition of carbon, 2 carbons, each carbon is 12 grams per mole. That's 24 divided by 30 times 100 gives us 80% carbon. So pretty easy. Okay, so what we're going to try and do here is try and figure out the molecular formula of a compound based on what we know about the mass of this compound. So, for example, we happen to know that a pure compound is made up of 2 grams of carbon and 10.7 grams of sulfur. So what is the molecular formula? And the mistake most new chemists make is they assume, okay, well, the mass has to be relatively proportional, so it must be C2S11. But that's incorrect because the atomic weight of carbon and the atomic weight of sulfur are different. And so because the atoms themselves weigh different amounts, we have to figure out what the actual number of atoms are for carbon and sulfur before we can figure out the ratio of atoms. So we need to change this to moles. Okay, so 2 grams of carbon divided by 12, or 12.01 grams per mole of carbon, 10.7 grams of sulfur divided by the molecular weight, either 32.1 or a little farther out, 32.07 grams. 0.334 moles of sulfur per 0.1767 moles of carbon. Now, the way you find a ratio is just the big number over the small number. Now, you can do this with the small number over the big number, but it's going to give you a much uglier ratio. I strongly suggest you always put the big number over the small number. When you do that, you see that there's exactly 2 moles of sulfur for every mole of carbon, so we could say CS2. Okay, a couple of quick points we want to make about this formula CS2. First of all, how do we know this even works? Okay, so we could prove this by going and determining the exact number of atoms of carbon, the exact number of atoms of sulfur we have. Okay, so their moles times the atoms per mole gives us 1 septillion moles of carbon and 2 septillion moles of sulfur. So this slide 56, is a totally unnecessary step. Okay, so but it does prove that this is true. There are in fact 2 sulfur atoms for every carbon atom. The second thing I want to point out is that this formula CS2 is what we call an empirical formula. It is the simplest possible ratio of carbon to sulfur, but we haven't actually proven the exact formula of CS2. And I'm generally not too worried about this. I haven't set up any problems where we figure this out, but the real formula of CS2 could be anything with the ratio of 1 carbon per 2 sulfurs. So it could be C2S4, it could be C3S6, it could be C4S8, etc. So those numbers below would all be possible molecular formulas, but the simplest formula, the empirical formula for all of these molecules I've written up, is CS2. Okay, take a minute and solve this problem. Find the moles of aluminum and the moles of chlorine, and then determine the ratio. And then when you're done, press play. This is pretty straightforward at this point. Find the moles of each based on the molecular weight on the periodic table. Then we see we have a ratio of 3 chlorines per 1 aluminum, so AlCl3. Again, find the moles, find the ratio, solve the problem. Okay, so again, the first few steps are the same. Find the moles of iron, find the moles of oxygen. Now I do want to point out that our numbers here come out very, very close to 1.496, or to 3 sig figs, 1.50 oxygens per iron. So the common mistake people make is they round that off to Fe1O2. But that's really not a good indicator of this ratio. The best ratio would be Fe2O3. That gives us exactly 1.5 oxygens per iron, and that best matches the ratio we have up above and the moles we have up above, and the fact that we have 3 sig figs of data. So when something lands exactly on the half, I strongly recommend you do not round up, but instead try to find a ratio that gives you that 1.5. And usually the easiest way to get there is to just double both numbers until you get whole values. Here's another example of that. Solve and find the empirical formula. Again, we get 2.5 oxygens per phosphorus. So that ratio is best distinguished by P2O5. So this is an example of a more advanced problem that you will often see in chemistry textbooks. However, it's also a common lab problem, and for those of you taking the lab course on campus, you'll find that this very closely mimics the empirical formula of an oxide lab. Okay. So we have 2.1 grams of copper. It reacts with hydrogen to get us 2.167 grams of an unknown copper hydride. So we don't really know very much about this product unless you consider the law of mass conservation. That says any matter that goes into a chemical reaction must come out with the exact same matter on the other side, which means the amount of copper in the product is the same as the amount of copper in the reactant. And so using that, you can figure out the mass of copper in the final product and the mass of hydrogen in the final product. If that's enough to get you started, go ahead and work through the problem. If you're still stuck, just keep listening and I'll go through the other side in 5 seconds. Okay. So if the mass of the product is 2.167, and we know that only 2.1 grams of that can possibly be copper, that means the mass of hydrogen has to be 0.067 grams. Okay, so with that, we can find the moles of copper and the moles of hydrogen, and sure enough, we end up with very close to 2-to-1 ratio of hydrogen per copper, and so that means the unknown copper compound is CuH2. From here, we move on to what's called combustion analysis, or what's also seen commonly as elemental analysis. They both work in similar ways, but this is the one shown in this book. Basically, what you have is a furnace, and you burn a very, very small, we're talking microgram amount of compound in this furnace. The oxygen is trapped and forms copper oxide. The hydrogen is trapped and forms water. The carbon is trapped and forms CO2. And so by weighing these compounds, you can figure out what percentage of your mass is carbon, what percentage of your mass is hydrogen, what percentage of your mass is oxygen, and you get this note back from the lab that tells you what the percentage of each of those things is. Okay. Now, I typically ran this problem as elemental analysis. We use nitrogen instead of oxygen, but we did this all the time. The simplest way to solve this problem is to just assume that since we had 100%, we had 100 grams. And if you do that, that makes the math here relatively easy. And this works because these are percentages by mass. And since we're just looking at the relative amount of moles, it gives us a perfectly clean number to work with. So we have 55.8%. We're just going to assume that 55.8 grams would exist if we burned 100 grams. And you find the moles. Do the same thing with hydrogen, find the moles. Same thing with nitrogen, find the moles. Okay. Now, we have more than one moles here. The trick to solving this is always take the smallest number. So in this case, that would be nitrogen. And from that smallest number of moles, we're going to determine the ratio of carbon to nitrogen and of hydrogen to nitrogen. Okay. So when we do the ratio of hydrogen to nitrogen, we find there's 5 hydrogens per nitrogen. When we do the role of carbon to nitrogen, there are 2 carbons per nitrogen. And so our formula can be C2H5N. Okay, here's one more problem. Go ahead and walk through this one. It's a little bit longer, but it's the same basic idea, and then I'll show you the answer. So again, the first thing we're going to do is just assume we have 100 grams of compound. So that means 61.31% would just be 61.3 grams divided by 12 grams per mole of carbon. That gives us 5.1 moles of carbon. For hydrogen, again, I'm going to use the 1.01 just because it gives us a more accurate value to 3 sig figs. 5.14 grams of hydrogen divided by 1.01 gives us 5.09 moles of hydrogen. We get 0.7288 moles of nitrogen and 1.456 moles of oxygen. Now, what we're going to say is that our nitrogen moles are the fewest, so we're going to determine our ratios according to nitrogen. So when we look at the ratios, we see about 7 carbons per nitrogen, about 7 hydrogens per nitrogen, 1 nitrogen per nitrogen, of course. You don't really need to make that calculation, although it's typically shown in most textbooks. And 2 oxygens per nitrogen, which gives us a formula going left to right across the periodic table of C7H7NO2. Now, the book is going to be a stickler for the order that you put these in. So you may want to flip back to the molecular section near the front of this slides to look at what that order should be. On the test, as long as you have the numbers correct, I will give you full points, right? So the order doesn't matter as much for me, but it does matter for MyLab and Mastering.